short introductory video on linear models. And basically, it's a simplistic idea, and you've already done it, but I wanted to be a little bit more detailed about what's going on. This is a graph of hours down here, and this would be distance over here, generally in miles in this case. And all it is basically, you've been on the road for a certain amount of hours, and the y-axis would be how many miles have you driven. And linear means that it has a straight line relationship. Another possible graph would be this down here would then be miles, and the y-axis in this case would be gallons. So here we're talking about how many gallons of fuel a car has, and as you drive further and further, the amount of gas in your car goes down in a nice linear fashion. So what does it mean to be not linear? Well, this would be a graph of a not linear situation. This is compound interest. Started with $150, and as time goes on, the amount grows and grows. So there has to be a way of looking at just numbers rather than the pictures and kind of determining if something is somewhat linear or not necessarily linear. So one way of looking at that is the idea of what does it mean to have constant change. So if I take a rectangle and I attach one corner of it to the graph anywhere and drag it to any other point on the graph, I get a nice little rectangle here. Now if I choose a different point, two different points, and make maybe even a bigger rectangle, you'll notice that these two rectangles look really, really similar. We could do it on the downward slope one. So if I take a really big one in this case, start one corner on the graph and end with the opposite corner on the graph, and maybe make a smaller one over here, that the two rectangles seem really similar. They're just different sizes, same general shape. But if we look at the compound interest situation, we can start off with a relatively big rectangle down here, and then choose a new rectangle up here, and you see right away that those two rectangles are not even similar. They're actually facing the wrong direction. The other two rectangles that we were drawing earlier were always facing in the same direction. This one looks very vertical looking. This one looks kind of horizontal looking. But the exponential graph, you have a horizontal down here at the bottom and a very vertical at the top. So this is kind of an indication of the idea of slope. Here, the slope of the line is constantly changing, and in fact, it's actually growing. So let's go back to our first picture and formally define slope. So what slope is, change my color here to red, is the ratio of the length of this side of this rectangle compared to the length of this side of the rectangle. You've heard of rise over run. I usually call it change in y over change in x. But basically that's all it is. It's the length of this side over the length of that side of the rectangle. I write it out this way. The little triangle just means change. So this would be change in y over change in x. How far did you go up and how far did you go over? In this case, it's a positive up and a positive to the right, so this slope is positive. It's going uphill. Rise over run is another way of saying it. Rise is the change in y, so you start at this point here and you change in y in that direction, and then you change in x in that direction. Y's are always vertical motions, x's are always horizontal. So this little ratio here is exactly the same as the ratio of this side, the length of it, compared to this side. Kind of like if this one over here was up 2 over 1, this one possibly, well, actually that kind of looks like what it is, up 2 over 1. This one would be up almost 1, 2, 3, 4, 5, and over 2.5. And if you set up the ratios of 2 over 1, this side being 2, this side being 1, and 5 over 2.5, you get the exact same answer. Both of them reduce down to the number 2. So these ratios are just equal as we move these different rectangles up this line. The same thing happens here, except instead of going up from your initial point, this one is actually going down. And then we're going to the right over here. So this would be a down right kind of slope, so that gives you an idea that it's negative, and therefore as you move left to right, you're going downhill. I always refer back to the stock prices. If you have this stock, you're happy because your value is going up, so therefore your stocks are increasing. And here, if you have this stock, then your stocks are decreasing. So this would be like a negative slope. All right. And the ratio of the big rectangle compared to the small rectangle is exactly the same. It's going to be negative, and it's going to go down at the same ratio, change in y over change in x. Let's see, this one's going down 1, 2, 3, 4, 5, 6, about 7. And then it's going 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right. So this would have a slope of negative 7x. If we look at this one, it's going down 1, 2, 3, and going over 1, 2, 3, 4, about 4. So it's about down 3 over 4. And if you type both of these into a calculator, and remember, these are approximations, these aren't perfect. I'm just using the graph to kind of thinking about what this is. This one here on a calculator is negative 0.77777, repeating forever. Negative 3/4, of course, is negative 0.75. So these are relatively close, even for an approximation. So as we keep drawing these rectangles, we would expect the slope to be around one of these two numbers. I think the real slope I made was, I don't remember. All right, so if we look at this one here, you have a small upward tick here and a longer x tick. So that means your change in y is, let's see here, approximately 1, 2, 3, 4, 5. Now from this point to the next point, that's downward, so I would call that negative 5. And then it goes to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 13. So the slope here is negative 13 because we went to the left. So the slope is actually positive. It's going uphill. So on this interval, this little portion of the graph, we have a slope of 5/13. It's not exactly shooting up. It's gradually growing. All right, let's see if we can do this one with the positive side. So this is going up here, change in x. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this side would be 16, and over here you got 1, 2, 3, 4, 5, 6, 7, 8, 9. So here the slope, change in y over change in x, would be 16/9. Now these are majorly different. This 5/13 is really small, it's under 1, and this 16/9 is almost 2. So there's a big difference, and if we found all the slopes going up this way, we would find that they were always increasing, always getting bigger and bigger, approaching that 16/9, and I imagine after this it would even get steeper. All right, so a formal definition of what slope is, we'll start off with a simple example. Just a couple ideas. Number one, this is a positive slope. As you move from left to right, it's going uphill. This would be a very boring stock price. It's not going up, it's not going down, it's flat, it's called constant. And a slope that would be going downhill, as one variable gets big, the other one's getting smaller, this is considered a negative slope. So when we're talking about slope, me get my little rectangle back in there. There it is. Let's change its color. Green. When we're talking about slope, all you need is any 2 points on the graph. So we could be talking about this coordinate here and this coordinate here. And once you have them, let's call this one 2, 3. Looks pretty close. Let's call this one 6, 5, even though it's a little too high. Then to find this distance, what you're doing is you're subtracting the y values. It's 5 minus 3, better known as 2. So to find the change in y, you're literally just going to take this y values and subtract them. y1, y2 minus y1, or y1 minus y2. The only thing you have to be careful about is when you choose change in x, you have to keep exactly the same order in your points. Here we're going y2, 5, minus y1, 3. So when you start with the x's, you have to go back to your first point, and it'll be 6 minus 2. So this would be x sub 2 minus x sub 1. Now technically you don't have to go from the second point to the first point. You can go from the first point to the second point. It gives you the exact same answer. So in this case it would be 5 minus 3 for y2 minus y1 over 6 minus 2 for a grand total of 2 over 4, better known as 1/2. Now no one ever believes me saying that you can just switch the order and get the exact same answer, so let's switch the order. We'll go 3 minus 5. So we're starting at the bottom point here, y2 minus y1 and subtracting y2. But once I choose that 3, it forces me to choose the 2 first for the x's. So here I get 2 minus 6. Well, 3 minus 5 is negative 2, and 2 minus 6 is negative 4, and when you reduce it, it becomes positive 1/2. So the slopes are exactly the same. Doesn't matter which one you pick first. Alright, so that's slope calculation. Most of you remember y equals mx plus b, so I'm not going to spend a lot of time on it, other than to say that m here really is the change in y over the change in x. It's the slope. Now don't be looking at the x, it's m, the coefficient of x, that tells us what the slope is. B is considered the y-intercept, it's where it hits the y-axis. I'm going to get you into the habit of writing the y-intercept as 0b rather than saying the y-intercept is 3. So it'll be like 0, 3. Alright, so if I get a graph, I'll just steal one here, and I want to graph something simple. Let's go blue. What would fit on this graph? Y equals negative 1/3 x plus 7. So this first number, this coefficient, I always try to write my x term first, so I always recognize where the slope is. This represents the change in y over the change in x. Oops, here we go. And this says it's negative 1/3. Now, if it was just a whole number, I would write it over 1. So if it was like a slope of negative 2, I would write negative 2 over 1. So I have a physical number for the change in y and a physical number for the change in x. The number over here, the 7, I'm going to write as a coordinate y-intercept. So x is equal to 0, y is equal to 7. And the first thing you do is you find the location of this graph. It has to go through a specific point. Lots of lines exist with a slope of negative 1/3, but only one of them goes through the point 0.07. So I'm going to plot 0.7. That's where I'm going to start. It's on the y-axis, 0 along the x, and straight up 7. Having a slope of negative 1/3 means your change in y is down 1, your change in x is to the right 3, Positive for the x's to the right, negative for the x's to the left. So from here, I'm just going to go down 1 and right 3. I'm not going to make any marks. I'm just, counting. So here's 1, 2, 3, and you plot a point. And then you just continue the pattern. Down 1, right 3. And 3 points is good, but I like doing a lot of them, to cross the entire paper. And let's see if I can get this program to draw me a nice line through those 3 points. Where is it? There it is. So if I start here and draw a line, it should go perfectly through those 3 points. And that would be the line y equals negative 1/3 x plus 7. Now don't get too attached to having a y and an x in your formula. If we're talking about distance, we might want one of the variables to be d. We might want the x to be t for time. So x and y are basically variable placeholders. For instance, back to a problem that we did in the previous section, George is going to put $500 into a simple interest account that earns 8% APR. What is the slope of this line? Now, a lot of people, they jump right on, oh, it's 8%. But you have to think about what are you going to get out of an 8% APR when you're putting away money? What are you interested in? And one thing you could be interested in is future value. And future value has nothing to do with a percentage. So one way to kind of figure things out is determine what your variables are. So here I'm interested in future value, and it's going to be based off how long I keep that money. Let's assume it's like borrowing money from grandma. How long I'm going to keep that money. So the longer I keep the money, the more money I'm going to owe the simple interest account. All right, so we have this idea that we have this f and the t. Now, depending on what you're looking for, you might want to find out the time it takes to get to a future value, but more commonly would be how much money do you have after a certain period of time. So when we do that kind of setup, and we're looking for a, y equals mx plus b, this becomes the change in y, this becomes the change in x. So here for m, we're looking for a change in the future value, which is measured, by the way, in dollars, over a change in time, which in this case is measured in years. So we need the slope to be change in money over change in time. The easiest time frame to talk about is what happens in 1 year. And if it happens in 1 year, it's going to successively happen because there's no change in this formula. All right, so I usually think about, let time equal 1 year. What's my change in my future value? In other words, how much interest do you earn on $500? So we can go to I equals PRT. And I, in this case, is how much that $500 is going to go up. So 500. Interest rate is 0.08. And time we're looking for is just 1 year. So let's see here. 500 times 0.08 for a grand total of 40. So my future value is going up $40 every single year because the slope would be constant. So m in this case is 40. All right, so that would be the slope of the line. Now, what is the y-intercept? Well, that's when t is equal to 0. Well, if t is equal to 0, you're not gaining any interest, therefore your y-intercept is how much you put away. So in this case, your y-intercept would be 0, 500. And to write the equation knowing your slope and your intercept is real easy. This would be f equals mt plus b. So the future value of this account is going to go up $40 every single year, and it's going to start at $500. And using this formula, you can find out how much money is in your account at any time period. 1 year, 5 months. Like if we were going to do 5 months, of course, t would have to be 5 over 12. All right, one last one. This is the tricky one. Margot's car gets 24 miles per gallon. At present, she has 13 gallons of gas in her car. What is the slope of this line and what is its y-intercept? And when I say y-intercept, I mean the vertical intercept when it hits the vertical line. So what are we interested in here? Are we interested in how many miles per gallon her car gets? Well, no, that's kind of a constant. Well, we're assuming it's a constant. She has 13 gallons of gas in her car, and she's going to drive someplace, I would imagine. So my question probably would be, how many gallons of gas are in her car after a certain trip? So what we're looking for here is an answer in gallons. And we're going to be talking about a certain distance that she's going to travel. So the line I would set up would be G equals MD plus B, where M, of course, is the slope, and B is the vertical, in this case, G-intercept. All right, so I need to find the slope of this. So I have to know what happens if I travel, well, let's say 1 mile. So if I travel 1 mile, how much gas do I use? Well, this thing is in miles per gallon, so that's not really helping me. Because if you remember from conversions, this would be 24 miles, this would be way at the beginning of the class, per gallon. You could set it up as a fraction. And if you're going to multiply it by something, and by the way, you're going to multiply it by distance, you'd be multiplying by miles. And if you remember the beginning of the class, the miles aren't going to cancel in this situation. I need miles to go away with what's in the bottom. So I'm going to have to take this fraction and flip it. So this is going to be, I can do 1 gallon every single 24 miles. And then if I multiply by 1 mile, what will happen is, the miles will cancel, and you're left with 1/24 of a gallon. Now, you have to really think about this. As you travel that mile, are you gaining a gallon per every 24, or 1/24 of a gallon, or are you losing it? And as you drive, obviously, you're going to be losing it. So it's really important to get the sign of this number in here. That's method 1. Most people aren't going to like that. So another way of doing this is to kind of take all the information, the 13 gallons and the 24 miles per gallon, but still realizing you're losing 1/24 of a gallon every. Don't do that. Just do this. All right, so our formula is going to become G is equal to my slope. I'm losing a 1/24 of a gallon every mile I drive. And then my y-intercept is going to be, what did I start with? So in this case, the y-intercept would be 0.13. So this would be 13. And here, depending on how many miles you drive, it'll tell you how many gallons are left in Margot's car. And eventually, of course, she's going to run out of gas, so it's not a continuous D, it stops eventually.